I'm Meena Choi from the Orgabitex group at Purdue University at the Department of Statistics. I'm a developer for the msstat. I have been working with like 2 years around, and I'm really happy to introduce the msstat to all of you. And we have a lot of number of the users increasing to use msstat. So I want to really explain actually what you can do, actually what you need to check before your correct conclusion for your research. Let's start with introduce the msstat first. So first I will introduce the msstat, and then second one you need to concern for the right use of msstat, and then how you can get the msstat from we have a multiple source to use the msstat as an external tool or R document itself. So I will introduce how you access this one. So first start with the msstat. So how many people have you heard about the msstat before? Oh, pretty nice. Quite a lot of. How many people already start to use msstat? Oh yes, great. Okay, so I hope that we have more user for the msstat in the future. So msstat is a statistical tool for quantitative the mass spectrometric proteomics. So this is the open source R-based package. So if the R is free, so you can download the R anytime and anywhere you want, and you can download this package. So this is a free, so whenever you want, actually you can, if you are interested, actually you can change the update your function in the msstat also. So quite, very open sources. And this is for statistical relative quantification of the peptide or protein level statistical analysis. So this the application note for msstat is already available in the bioinformatics. And then we also have another MCP papers, more the statistical background, what the msstat use. You can see the link in the also msstat the web page. First, I introduce what you can do from the msstat. So three main tasks you can do. The first one is test the protein for different abundance or the peptide for different abundance. This is the main task. So which means you want to get the conclusion like this specific protein or peptide actually significantly different between the group or time point you are interested in. And second one is quantify the proteins in a biological sample, which means we got the quantification number for each sample or each, the subject you are interested in for the downstream analysis for classification or any other, the next downstream analysis. The third one is design of the experiment design for your future experiment. So I will more detail explain about what actually you can do it. And this is quite the most frequent question. So what type of experiment MS can handle it? The first one is labor-free workflow, which means labor-free SRM. And then the label-based workflow, label-based SRM, which means stable, the isotope label reference peptide. And DDA, or shotgun data. And then DIA, or the SWAS data. So people are quite interested in they can use the SILEC data or iTrack data or TMT data. We are not ready yet, but we are still start to working for the SILEC data, and more want to look at more the PTM data. So we are gonna give you more suggestion very soon, but not ready for iTrack data yet. So, but you can keep posting what our the new release or what is our new aspect in the ms.org. And so you can see what is updated for, and what kind of the comparison you can do. So this is more different type of experiment design, like group comparison. These are the disease versus healthy. We call this is group comparison. And time point comparison means for one specific subject, you have a multiple measurement for a different time point. So you want to compare 0 point and after 1 hour or after 4 hours. So you want to compare how much difference between the two time points. We call this is time point, time courses design, or pair design. For some specific subject, we can take the sample from healthy cell or cancer cell. This is a little bit different, the group comparison, like the healthy versus disease means disease group. Like all the cancer cells only take the cancer cell from diseased person, and take the same cell from the other healthy person. Like there's a different subject group. But paired design means for specific the subject we have like multiple of the samples. So these three different types of experiment we can handle in the MSStat. So this is just a brief overview what type of experiment we can do from the MSStat. So and then I will just go for like what kind of workflow actually MSStat do. Like here is what the overview text show the workflow the experiment. First, experiment design step means you set up your hypothesis. What are you interested in? What kind of conclusion you want? You want to compare like disease versus healthy or something. And what type of experiment you will do, like DDA or like SRM or whatever. And then how much sample you can take it. Like, and then you need to concern like blocked, randomized design what actually in the morning section discussed. And then you set up the design, and actually you did actually the sampling and you processed all the sampling preparation, and then measuring the something, and then finally you get some numbers. Now at this point you're ready to do something for statistical analysis. So this is the starting point for the MSStat. And MSStat required this information. So like this 10-column information is required to start the MSStat. This format is automatically can generate from the Skyline. But if you use a different spectral tool, you can, if assigned like this column, you can just go ahead the MSStat. The first one is protein names, and peptide, and precursor charge, and fragment ion, and then product charge. For like DDA data or the other data, if you don't have like this information, you can just put NA. So like you don't have this information, but it doesn't matter. You can go ahead to the next process. And the labels, like label heavy label or light label. So if you have only endogenous one, you can just put the L, like you don't have any H here. And then condition, like healthy, disease, or time point 1, 2, 3, 4, depending on your design. And then biological replicate, like you need to assign that this is the same subject or a different subject. And here run is MS run, and then this is a final intensity value for data processing tools. So if you have this format, and you need to start to statistical analysis. So first, actually this is the main step for statistical analysis, get to conclusion. But before, we need to check the quality control and normalization step. And also you need to double check before actually you need to get your correct conclusion. And then this one is the last step. So each step, the MSStat have each functions and each visualization. And then this bottom one, we can use the MSStat as an external tool in Skyline. And then there are three main functions. And then this is the name of the function in the Skyline. The QC quality control handle this step. A group comparison function handle the modeling and then generate the conclusion and visualization step. And then last, design sample size can handle the design of the next sample size of function. So let's go over each step what you can do. So I will go forward as external tool, but this is really similar as what you can do in the MSStat in R. So that is more options and more detail. But for beginning of the user, or usually the user of Skyline people, we assume is not familiar with our common or computer common and programming. So we just start with these external tools. So the background, actually the beginning of we introduced just develop external tool. We have our Skyline tools. We work really close with the Skyline teams, and there are really a lot of the connection. And then after we make automatically just generate the report and then just use the MSStat. But the idea came with, how about we just use the MSStat just in the Skyline, not the separate to program. And it's going to be really easy if you have like the interface, user interface. That makes more easier to user. So that's why we start to develop the external tools, and they make everything just simple. So now we are kind of the developing step. So we have our external that only does the default option, but we can expand as much as you can. So here, if you install the msstat, now we have a three function, what we discussed before, like QC, group comparison, and design sample size. So the QC step, doing the data processing the data, and then generate all the visualization, and then quality control and normalization, and group comparison, comparing the group and drawing all the visualization for your conclusion. And then design sample size, also calculate all the sample sizes, your the futures. So if you you have to follow this step. So click the first QC. Okay, so just before, how to install this one. Click under the tool, click the tool store, and you can see these windows pop up. And here there are multiple, the external tool already existed in the Skyline, and msstat is one of them. If you click it, you can see all the information about the relative, the msstat information. The organization and what language we need, R and C+. And then if you want more information, please visit the website, and then description, and then here is the what version we have. And if you click the install, they're gonna start install all the required one. First, start with the if your computer doesn't have R, start to install R, and then install all the required package, and then msstat, and then it will be ready. If we are update the new versions, what you can see here, there will be like the red, the circle, the arrow thing will be pop up, which means you need to update it. We have an updated version, and then in that case, you can see like reinstall or something, and then if you click it, they automatically install the next version, like the newest version. And then if you click the QC, the small windows pop up. So which means you need to choose a normalization method, one of them. But that is based on your experiment and your assumption you need to consider. The first data processing is not considered like this normalization. Always we need to do this one. Generate all the report file, which means the input structure from the in Skyline, and then we do the log 2 or log 10 transformation of the intensity. Because all our statistical model is based on the log transform intensity. So this is just a default option we need to do. And then you can assign the one of four. So first one is none. You don't need to normalization. And then three of them, you need to think about which one is most suitable for your experiment. The first one we call the equalized median. Sometimes we call constant normalization, which means we make the constant or same median of intensity across the run. If you have a label-based SRM, you can assume the reference peptide, we just put the same amount. We can assume this one should be the same across the run. So we can make the same median reference intensity across the run. But if you have a label-free experiment and then click the constant normalization, they don't have a reference intensity. In the cases, we use endogenous intensity. We make median of endogenous intensity across the run. It could be the wrong. It's really hard to make assumption. That means all the median of the across the endogenous is. We need to think about it. This one is actually could be same or not, because if you use the different normalization, which is not good for your experiment, maybe your conclusion will be changes. Right? And then quantile, the difference is between constant and quantile is here we make the median is the same, but here we make the distribution of intensity will be same. I will show you how this is working for the visualization one. But the difference between two, the quantile is more suitable for the data which has quite large number of the measurement of specific, the certain runs. So distribution, for example, if you have only 10 measurement, and then you make the distribution is like equally across the run, is maybe hard. But if you have like thousands or tens of thousands of measurements, it's more makes sense that this distribution among the larger number of the intensity is across the run. So you need to think about it, which the data set, what kind of experiment you use in your data. The global standard normalization is more suitable for the label-free experiment because this one is we can apply this endogenous intensity. The global standard means global standard protein or global standard peptide that we can assume this amount should be same across the run. Like for example, like some like bovine serum, like protein or something, we can assume this one should be across, this amount should be across the same. Depending, it doesn't matter like which condition you have. At that cases, we make that protein make intensities the same and then apply this shift to the proteins. So label-free experiment, we recommend you some spike, the global standard, or you need to know some protein should be the same. So this is relatively suitable for constant or the quantitative normalization for the label-free experiment. So if you choose one of them and then click OK, they generate the report from the Skyline and then do the normalization and then generate several visualization plots for quality control before you start the statistical analysis. I will explain the visualization stuff because that is really important. Usually what we are worrying about the external tools, it's really easy. Just click OK, and then just click OK and click OK, and then the result is the same. And then there's, okay, this is from msstat, I don't care. But like the result is what this totally opposite what expected. But actually, if not checking your quality control, we don't know. You need to know what assumption is more suitable, or is there anything wrong happen in your data set. So I will just go over like some of the cases, which point you need to concern. So if you click it, like there are three, the visualization will be generated. First one is we call the quality control plot, and second one is a profile plot, and third one is condition plot. Each one have like some different aspect we can check it. The first one, I will go the quality control plot. This is a box plot. So this is a summary of all the measurement for experiment. For example, how to read this one is here, this is the MS run. And here is the load to intensity. And here's the reference panel. And then here's the endogenous panel. If you have a label-free experiment, you don't have this reference panel. You have only this endogenous panel. And then you can see this is the condition number 1 to 10. If you have a healthy and disease, probably you have a healthy panel and then the disease panel. And this is we call box plot. So this is show the distribution of all the measurement, and this point is each intensity. But middle part we have a lot of the point. So this box show the middle line show the median of intensity for this specific run, and then this box means 25% quantile and 75 percentile of the intensity. So we assume like, okay, this is before the normalization. They have even the reference. They have a little bit up and down across the run. Like this is just mass spectrometry, the variance. And then endogenous also have like here's a row and here is the little bit up. If you use the constant normalization, what I said, we make a median is the same. So here now you can see this median line is now this is equal. The quantile normalization means we make the distribution is same, which means we make this box make the same. So just up and down a little bit shift for the reference, we just exactly apply to the endogenous one. So this is the effect for the normalization. So this box plot is really good to check how your normalization method is working, and then also see how much its variation is different. For example, this is relatively really good quality of the data. But sometimes some specific run, like some specific box, is really up or really down. In this case, you need to double check actually what happened. This specific run is relatively really low than the other one. So this is really critical, the point to check things. For the endogenous experiment for normalization, let's assume we don't have the reference panel and we have only this endogenous one. This is before normalization. If you use just click the normalization for the endogenous one, we make this the median is the same. So now you can see this 5 condition is lower than the other one. But if you just make the same, actually this distribution going up and is everything is make the similar one. So in this case, maybe conclusion for here to here is quite different. But if you just use the normalization for label-free cases, maybe actually their distribution is disappeared, and then your conclusion is like just the same as before. So that's why we need to consider your normalization is suitable for your data set. And next one is the profile plot. Actually, I really like this plot because this one showed individual measurement. So before, this is all the summary of all the measurement, but this is per each proteins. So that is each measurement, and then we make a line for each the transitions. So color is peptide, and then the line type is a transition. For example, here the red, the peptide have 3 different transitions, and you can see this peptide is a little bit higher than the black peptide, and they have the black peptide have a little bit more variation than the red peptide, and so on. So this is really good for check actually your quality of the data. So for example, this is one of the good quality, and this is another example. Another proteins, and there are 3 peptides, and green one is quite consistent across the run, and then you can see this red peptide have a little bit shift to the other run. You can check out probably there are something going on this specific the transitions. And another protein, you can see here is relatively the connected all the runs, but here you can see they are disconnected, which means they have a missing value. So this is also good to check how much missing value you have. So this SRM cases is relatively okay, but for the DDA data, it's important to check the missing value because relatively we have a more missing value thing. So you need to think about a little bit more depending on your data set. So the profile plot also you need to go over, like after generated, just go over all the plot or there are something significant changes or something wrong. And if you have something wrong, you need to just go back to what actually happened in your measurement itself. So I will just go over a little bit more for a specific data set. And this is the condition plot. This is also before your analysis. This is just descriptive purpose. Just show the potential systematic difference between the group. Like different group, we just use the label cases, take the ratio, and then put the mean, and then show the confidence interval. So you will have some idea like how your testing result will go. So yes, so now you're done. You checked all the quality controls, and then you seems like your data seems quite ready to statistical analysis. So let's go to the statistical analysis. So click the second option, group comparison, and then this pop-up window will be appear. So this function is test for the different abundance. It's most main task of the msstat. The hypothesis is there any difference in abundance between 2 conditions? So basically log fold change is 0 or some numbers. If you have a window here, first you need to decide the name of the comparison you want to see. So let's assume in this case we have a 3 condition, 0 hour and 6 hours or 48 hours. I want to compare 6 hours versus 0. So here I put 6 hour minus 0 hour. And then I want to use the median normalizations. And then here, the control group is the 0 hours, and which one you want to compare. So I just click the 6 hours, and then they are compare 6 hours versus 0 hours. And under that, there are several options of what actually we can do in msstat. First, include the reference. Then that means you have the label-free or label-based experiment. Like here, label-based experiment, so I just check the click. And here, the assumption is equal variance and include the interference transition, and there are scope of the experiment. So this is kind of the most important part of the msstat, and this is kind of unique task compared to other statistical tools based on the linear mixed model. The first one, assume equal variance, means, let's go back to the profile plot. The equal variance between the feature means each transitions. We want very equal variance. Here, the red the transition have relatively parallel, like there are really similar bounds between the rows. And then here you can see the black line is a little bit more fluctuation than the red one. So this is kind of what is equal variance or unequal variance. If they have a really similar parallel things, means equal variance. If they have one thing is really parallel, but the other one is a lot of the fluctuation, that means this variance is bigger than the transition. That is how to distinguish these terms. So usually SRM experiment, we can expect quite relatively the similar one, but DDA data or SWAS data, we can see they have more fluctuation between the transition. So this option is assume the equal variance for depending on your experiment, what assumption is correct or not. And the scope of the biological replicate and scope of technical replicate, this one is also very important. So scope is we can have two options. One is expanded and the other one is restricted. Restricted means our conclusion is restricted this specific sample. Like for example, we have a 5 sample for each condition. Our conclusion is significant among these 5 specific subjects. That is a restricted. What is expanded means we consider a more variation. So that's why our conclusion will be different for the population level. Like we can expand our the conclusion not for this 5 subject, for more healthy population. So this one is the 2 different one. So what you need to consider, if you have a very small number of subjects, like only 2 or 3, even though you can use the expanded, it's hard to guarantee only from 2 samples you want to guarantee the whole population. It's really hard. So if you have a relatively large number of samples, like 100 or like 200 for each group, maybe we can more guarantee to our conclusion is population level. So this 2 is based on this scope of conclusion. So because we are using the linear model, and then we can consider like this the random like variance term, you can expand our conclusion to the population level. So I will just show how it's going to be different effect to your conclusion for with one of the data set. So choose one of them. And then what actually msstat will do is actually they are just automatically distinguish what kind of the model is suitable for your proteins. So this is just a partial one. Actually, msstat have like 55 unique different models depending on your experiment. I don't want to explain more detail, but I just want to house a difference. For example, these general cases, group comparison have like this one, and then time courses have a different one. Like the different design, we need to consider a little bit different models. And some specific cases, for example, if you have only one single feature or have a lot of missing value, like some specific situation, we have to use more simpler model. So msstat just automatically consider all the possibility and then use the best suitable model for each protein or each peptide. So in this case, you don't need to worry about it, but like there are something going on inside it. Okay, so if you click this one, they are considered this model and then we'll generate the older result. But you need to consider like your assumption is correct or not. This linear mixed model, here the last term is the error term. In statistical method, this error term we assume always normality, like normal distribution or bell curve or something. This one is if you actually your data is unequal variance, but if you choose the equal variance assumption, actually this one is not correct answer. So if you click it, there are two different plots to verify your assumptions. So one is the residual plot, and the other one is QQ plot we call. Let's see one of the examples. Here, one of the proteins, the profile plot. You can see this reference panel. The red transition is relatively quite consistent, but here you can see some of the black transition have, more up and down and up and down, which means they have a more variation compared to the red one. So if you use the msstat generate the two plots, so let's see the residual plot what happened. So this black line generate this much broad range of the residual, but relatively the other one is quite smaller one, which means we expect this one have really similar pattern across the route, like similar the range of this. But here they have a really different range. We can also confirm this one from here. We expect, like this 4 panel, we assume really similar slope is guaranteed of normality, but here 2 line is quite deeper. Means this you can match this color, like the green one has more deeper, and then the next white one is a little bit less deeper, but still deeper than the other one. So we assume this one 6 have to be very equal, but the other 2 is quite different than the others. This means it should be the unequal variance. Yes.
Yeah, I just wanted to maybe rephrase this a little bit and comment on that. So what the models do, they try to explain some of this variation from what we know about the experimental design. For example, we have reference peaks and endogenous peaks. We have healthy group and we have disease group. We have subject 1, subject 2, and so on. And then the residuals will be whatever is left unexplained. So essentially you take the intensity, you subtract what you expect to be explained by the systematic part, and the residuals is the leftover. So we see that for lower predictive intensities, there is more variation, so there's more unexplained part than for high intensities. So it means that there's more unexplained variation in lower intensities. So this is what it means that we have unequal variance. So for low intensity fragments, there's more variation which is not explained. And you can see this on the residuals. So if you have the same spread of residuals through the whole plot, it means that equal variance is appropriate. But if you see things like that, in kind of megaphone shape, it means that it's unequal variance. So you already see this from the profile plot. It's just another view on the same thing. So it's just complementary. And then on the right side, somebody asked me during the break how often the assumption of normal distribution is appropriate. So these plots, they're very frequently used in statistics in general to diagnose if normal distribution is appropriate or not. So on the x-axis, you have the values that you would expect from normal distribution. On the y-axis, you have the values which we see for these residuals. So essentially, if it's a straight line, it means that normal distribution is okay. If the points kind of deviate from the straight line, it means that normal distribution is not the best choice here. And so oftentimes, this deviation from unequal variance kind of looks like deviation from normality. And so sometimes people say, oh, we cannot use t-test or we cannot use linear model because these lines are not straight. But what happens is that you just have different fragments which have different variance. So if you draw these lines separately for each fragment, you see that normal distribution is quite all right. It's just the variance is different for different fragments that you need to account for that. So this really discussion is just to diagnose everything that happens after we accounted for the experimental design.
Yes. Okay, so now we checked all the assumptions and we are happy for this. And then this is the result. So if you click the OK, like this result CSV file will be saved under the folder your file has. So for each protein, and then like this compares to what you desire, this is the estimate the log 4 changes, and then consider like all the FDR, and then here is our final p-value. So basically here, this is our practical difference significant, and here is more statistical difference. And then with this conclusion, we also generate the 3 different visualization. The first one is Volcano plot with this log 4 changes, and here's just p-value, and here we go. So for each comparison, like 6 hours minus 0 hours, this one summarized all the protein is where's the position. So here, if higher, here's we use the minus log, so smaller, very close to 0 will be really higher numbers. So upper means more significant, and the the lower means less significant. And here is the cutoff value. For example, here like 0.05, like most popular the cutoff for significant values. And then here is the log 2 for changes. So if you go to the right panel, like or the left side, which means more of different for changes. The red dot means upper, which means 6 hours is higher. And then the blue one is down-regulated, which means 0 is higher. Like 6 one is like lower intensity. And this is per each comparison. And there are 2 more visualization. One is the heat map for each protein, and then all the comparison you want. So this is a summarize all the comparison and then all the proteins. So still red means up-regulated and blue means down-regulated, and then you can just classify actually which protein is more similarly changes and which one is like differently changes. And the other plot is a comparison plot. This is for certain proteins and across all the sample. Like for this specific proteins, how is it working across the different time point and so on. So a little bit with the same result, we have a little bit different visualizations provide. So what I mentioned, like scope of conclusion is based on your decision, not for the model and everything. I just want to stress out how it's gonna be affect your conclusion. For example, like here I do 48 hours minus 0 hours, and here I use the restrict terms, which means our conclusion is more restricted for these specific samples, and I use here expanded terms, more the population level conclusion. You can see there are really a lot of the number is really significant here, but you can see the other cases, the expanded cases, that's a little bit less significant. So it's depending on your choices, what kind of the conclusion you desire. So based on your desire, you can see a little bit less sensitivity or less specificity. That is your depending on your decisions. So yes, now we are done the group comparison part. So the last stage for your next experiment. To calculate the sample sizes, we need to know how much variation we can expect. In this case, we use the variance estimate from this data set as a pilot study, and we assume probably the estimate that the variance is really similar for the future experiment. So take the variance, we calculate the variance estimate from this data set, and then calculate how many samples you need for this specific power you are desire. So for example, if you click the design sample size option, this window will pop up. So same thing, normalization method, you need to choose it. And then if you click the sample size, means I want to calculate the sample size. And with 3 peptide per protein you have, and 5 transition per peptide you have, and you want at least 0.8 power. Power means the probability to detect the true fold changes. And I want this range of desire. And for this setup, how many sample size we need. So if you click this, like this tables will be generated. For example, if you want to desire the 1.25 with the 0.9 power, and you have a 3 peptide per the protease and 5 transition per peptide, and you need 4 sample per the conditions. So with this table, we can generate this plot. This is just summary of the tables. Here, if you have a higher 4 changes, and this the relatively we are smaller the sample we needed. And this is also power calculation. Based on this variation, if you increase the 4 changes, we can guarantee the higher power. So depending on your experiment, you can decide it, and then you can calculate how many samples you needed for the similar experiment. And another thing, so which function you use, actually the msstats.log file will be generated under the folder you already have. This is really important to keep what options you use, and also if you have some problem, it's really easy to detect where is the problem came from. So here, what version what version of the msstat you use, and here is what options you choose. So you can check you have the option you want or something, and then you just it also show the process of this. So if you have some issues for installation, or you are not good, if you think maybe this one is not correct and you want to advise for us, maybe that this log file will be help to find where the problem came. So this is kind of the summary. What is the best option for different design of experiment? So DDA, SRM, DIA is the most 3 different design of msstat can cover. So this is the profile plot to show each characteristic of the design of experiment. For example, DDA data, usually we have only endogenous one. And here we have a peptide, and then lower abundance one, we have a lot of missing value. Here, like this specific peptide, there are no value for these groups. Probably really low, so that's why it's really hard to detect it. And then SRM, we have 2 panels, the reference one and endogenous one, and relatively not much missing value, and then really consistent across the run. In DIA cases, we have really a lot of the transition, and then you can see there are really high variance for the lower abundance one. So they have different characteristics. And in each cases, what option is the best for your analysis, and what is the normalization recommend for us? For normalization aspect, the DDA data, constant or equalized the quantile normalization is usually not suitable for the endogenous one. In these cases, we want to have you have the global standard, the peptide or proteins. And the SRM is especially if you have a reference one, constant or quantile normalization is really good for this normalization method. And DIA data, probably quantile normalization is working because we have really a lot of the measurement, right? So quite really like tens of thousands measurement for a specific run. And these cases, we can just use the quantile normalization. And the fourth option for the statistical analysis, for SRM cases, usually the equal variance we can assume the equal variance one. But for DIA data or DDA data, we assume definitely the feature on unequal variance should be working for this experiment design.
Meena, why for the DIA type of experiment you assume interference is false?
It's really hard to. What is the mic is for the interference terms?
Can you repeat the question?
How come for the DIA type of experiment, one would assume that the interference is false?
Oh, okay. So it doesn't mean that there is no interference. So it's more the interpretation of interference. So when it say interference is true, you assume that it's systematic, meaning that if you repeat the analysis, you will see the same interference.
Okay.
And it's true in SRM often because the experiments are well calibrated, right, and you know what you're looking at. In DIA, there's a lot of kind of stochastic
Random
events
interference.
happening, yes, and
Okay.
also some uncertainty in how they interpreted computationally. So what these interferences, they're still present, but we treat them as part of the random variation as opposed to systematic. So when you say interference equals false, you actually have larger noise in the system, so it will be more difficult to detect changes. And usually it's a safe thing to do generally, so if you are, even in SRM, if you think that some of these interferences are not systematic, just by the way you designed the experiment, maybe your assays were not well designed, then it's safer to say interference false, because then you would consider all of this as part of the random.
Yes.
Do you really prefer also in DDI data to use a global protein standard for normalization? And why do you do this? And wouldn't also the normalization of all, if you have a data set where you assume that most of the proteins you have are not changing, wouldn't that also work very well?
So in that case, it's probably quantile normalization. But still, I feel like DDA data have a lot of missing value. Like if you have an email, have a lot of things going on, like a lot of, it's like, even though they have a really relatively similar number of the measurement, but this is not from the same things and so on. So,
But what if your global protein standard has missing values too? Isn't it also awkward?
usually I assume like global standard is not that much missing value. Like they have of course the same amount. We can do something. Yeah, if you have a like global standard of missing value a lot, maybe this one is also not good enough.
Yeah, you know, there's no perfect solution.
Right.
So the question, if you haven't heard, it's quantile normalization versus global standard normalization. And they're both, you know, there are pros and cons for both of them. So quantile normalization was developed in the genomic literature, where you have thousands of features that you want to normalize. Usually in DDA, we have a smaller number of features, so whatever, it can overcorrect some of the systematic effects. So especially if you have a reasonable proportion of things which are actually affected by the stress, it can remove some of the true effect. But then you're right that if you use the global standard, if the standard itself is not very reliable, then you introduce more noise with the standard.
We have just seen if you really just work with a single global standard, like a single peptide spike in or a single protein spike in, depending on where in the chromatogram it eludes, you can sometimes introduce errors. So ideally, one should use several global standards.
And that's actually, we had some work where we have a combination of labeled references for some peptides and no references for other peptides, right? And you can kind of combine this information. These are more advanced methods already, but in kind of the basic level, it's a trade-off, right? So if you have a large enough number of features of the experiment, you can reasonably expect that only a small number of features will be changing. I would go for quantile, but if it's a targeted experiment where you think many of the features will be changing or the total number of features is small, I would go with one of several standards.
Yes.
Yeah, so to be in the safe side, wouldn't it be better to put always the variance to false, or is there any penalty in terms of sensitivity or speed for doing that?
For speed also?
Yeah, and that's the question. So,
Yeah.
I mean, you say that in SRM you recommend that the feature variance is 2.
Yes.
Yeah, but if I'm not sure if my
Yeah.
variance
Right.
is
Mhm.
it's the same,
Right.
so
And-
if I put false,
Yes.
do I am less sensitive or not?
No.
No.
If the unequal variance, if you click the use the false, if they have an equal variance, they just weigh the equal amount, so it doesn't matter. Like if
Okay,
they
it
have
doesn't
an
matter.
equal,
To be in the safe
Right.
side, if
Right.
you are not sure, it's better
No.
to put false.
yes, maybe if you're not guaranteed that one, is you can put the false, or you can use the true, and then check the residual plot or QC plot,
Mhm.
and then there are something significantly different. Maybe you can just go again and then just use the false. Yes, so it doesn't matter depending on the protein. If they are equally, they are just equally weighted, so it doesn't change this. Yes.
But the danger is that you can overfit a little bit. If you just happen to have some pattern where you have a few outlying intensities, unequal variance will overfit to them. Unequal variance will still force that you just have a single number. So if this happens, so the danger is you may be over.
So yeah, so just double check the residual. Yes. So yeah, so I will just demonstrate one of the examples. So what I just addressed. So here I have a label-free SRM data. The label-free SRM, they have two conditions. So one is disease and one is healthy, and then 7 injection and 3 replicate. And this is one of the examples the Brandon already showed in the Monday. We just process the Skyline and then just start to use the MSStat. And then I just, before start the analysis, I just draw the profile plot and then just go over, like just scroll down, like how it look like. And then I found the 2 or 3 protein probably we need to double check before we started. Here is the one of this. This is like inconsistent peptide one. There are 2 peptides, red one and black one. And red one you can see like relatively this one, and then you can see like here seems like disease is a little bit higher than the healthy. But black one you can see like there are really a lot of the variance, and then here's lower, and then there's upper. Like there's, even though 2 peptides are from the same protein, actually they are different pattern. What's going on? Actually we have no idea like in the MSStat like after we got the numbers. So in these cases we need to use the really good visualization for Skyline. So you need to go back and forth to use the visualization to check the quality control. So from here profile plot, I just look at the first red peptide in the Skyline. Here you can see quite relatively okay, and then there like the ratio is okay, and actually the chromatography is looks like this. And then I check the black one, and you can see actually their ratio is kind of different, and then there's none. And then actually when I checked one of this chromatogram, actually here it looks like this. A relatively really smaller number, and then it's really hard to detect which one is like, actually they choose this one, but like it's really hard to do it. So across the like this chromatography is something going on, like so measurement or something is really not, or I'm not sure. So depending on your decisions, you want to use both, or you want to just use this red peptide, or depending on like you want the black one. How is actually the conclusion is different. Here if you use only the red one, here you got the positive numbers, positive log field changes. If you have like this black one, it's really negative number, and then if you combine these two, and it's another different number. So if you do not check this quality and then just got this number, probably it will be wrong. So that's why we need to double check your visualization before you start the analysis. Here's another examples. Similar one. There are 3 peptides, and one is really consistent, and one is really different. Like not that much with the variance, but like consistently different. What's going on? Also, same thing. Just go back to the Skyline. Actually, I just checked. Actually, the measurement itself is wrong or not. Here, the red one, you can see is really consistent. Actually, the peak is okay. How about the black one? Black one is also really okay. Like it seems like the measurement itself is not a problem. Probably the peptide level there are something happen. But actually, MSStat does not count like what's going on here. In these cases, if you separate, if you have like choose a different peptide, you can see also you have quite different the log field changes. So you need to be aware of these issues. In these cases, probably if this is a label-free experiment, probably you can use a label base. So probably they have like this peptide have some problem, or they have some actually happen like phosphorylation or any other modification. This part is you need to be aware, and then you need to go a little bit dig after these issues. So please check your poor quality of data, and then I know there are some of the advanced peak picking program in Skyline. So if measurement itself have like check the different peak or something, actually this advanced peak picking program is actually correcting the measurement itself. So you need to check this one also. So this is just small examples, and there are several ways to access the MSStat. So definitely first you can use the external tools. here is the website from the Skyline. You can just download the msstat, or you can use the tool store what I show you. And this is really easy to just click, but I just want to be stressed out. You need to check the quality or check your assumption, and then more have the background of which one is correct for your data. And another way is you can download from the Bioconductor. This is R-based. So some people is really afraid of like how to use the R command or something, but it's really easy things. We already have R script. So you can just follow the R script and just change the number or file name, and then that's it. Like if you know which option have a different conclusion, just change the option and that's it. So if you can take the more advantage of a more option like visualization, size of text or size of graph or different color and so on. So if you want to start to use R, definitely I just want to recommend this Bioconductor one. And here is the msstat, the official website. Here we have a news and installation, all the manuals. We have like 50 pages manual for different design, what you have to consider, like due to what I present today. And then there are example data set and R script, so you can just follow it and then just modify based on your experiment. And there are msstat daily, which means as Skyline daily. This is a developer version, not the officially version. Even though I testing some function in my computer, probably different data set have the different issues. So this is just a developer version. So I just keep updating the whatever I fixed the bug. So this is the most recent version of the R. And also, I just want to announce we have a msstat Google group. So if you just register this one, you can get all the news from my side, or you can get all the question from the user. So this is more discussion and question and answer pages. So probably you also have same issues. Just searching if you have like some same issues, you can get the solution, or you can just post your question here, and then I will answer it, or the other people and answer it. You can share all the experience of the msstat here. So we already have several papers used msstat for their analysis. And then the future plan for msstat, we just start to working for the max quant output, more the DDA databases. So we take the output from max quant and then just generate the format for the msstat, and then you can just go over just work through the same workflow for your analysis. And we are just start to look at the SciLec data. So we are gonna expand the statistical model for the SciLec data. And then we also have a feature selection function, which means, for example, DIA data. We have a lot of the feature for each protein. Just take the most informative, the transition for analysis, and there is show the much better conclusion for your analysis. And the sparse the stat, this is for if you have only few reference peptide and other things just label free, we can just impute the reference one to get the better result things. So this one is another separate paper from the nature method, and then we are going to integrate this function in the msstat. So msstat is kind of the pipeline for mass spectromic proteomics. So we just plan to expand all different branch for different function things. So we are going to keep updating for the downstream analysis. Definitely we are going to improve the user interface in the msstat as an external tool in Skyline also. Yes, and that's it. So definitely the Brandon and Mekos lab members is our one of the favorite co-worker for the expanded our msstat, and then another Tina and Olga and then Edward, they are also really good suggestion for msstat for future aspect. And yes, I'm done. And do you have any questions?